We're presenting our work on skill transfer for temporal task specification. The problem is motivated by reusing prior knowledge, like learned policies, to solve a novel task in zero shot. We address the problem of learning policies from a set of training tasks that transfer to a wide variety of novel tasks in zero shot in the same environment without access to the transition dynamics. Our system takes as input a set of training tasks and a novel test task, and output a sequence of skills to solve the novel task. In this work, we use linear temporal logic, or LTL for short, as task specification. Many literature has successfully applied LTL to specify robotic tasks. A review paper in 2019 showed that 245 task specifications from 306 robotics papers can be expressed using LTL. LTL syntax is defined recursively. Atomic propositions capture environment states, like whether or not the light is on in this room, by mapping the environment state to a Boolean variable. LTL expands the operators of propositional logic not and or by adding temporal operators, next represented by the letter X, until represented by the letter U, finally or eventually represented by the letter F, globally or always represented by the letter G. The truth value of a temporal operator is evaluated over time. A satisfying trajectory of finally A means A becomes true at some point in the future. A satisfying trajectory of always A means A stays true throughout the execution. A satisfying trajectory of A until B means A stays true until B becomes true at some point in the future. Our proposed method, LTL-Transfer, has three parts. First, learning policies for state-centric options from a set of training tasks specified by linear temporal logic, LTL. Second, decomposing state-centric options to transition-centric options. Third, applying transition-centric options to solve novel tasks in zero shot. Given an LTL task specification, finally X and finally iron, which means collecting X and iron in an arbitrary order, in a Minecraft-inspired grid world domain. We first translate the LTL task specification to a reward machine shown here as a graph. The nodes represent reward machine states that encode the progression of the task. The edges are labeled by Boolean formulas. If satisfied, progress the task to the next state of the reward machine. We decompose the given LTL task to subtasks encoded in the reward machine states 0, 1, and 2. Then we can use any RL algorithms that solves LTL tasks to learn a policy for each subtask. The policy for the reward machine state 0 transitions the reward machine from the initial state 0 to state 1 or 2, depending on the proximity of the robot to the X and iron in the environment. Note that transitions in the environment induce transitions in the reward machine, which encode the task progression. Similarly, we learn policies for the subtasks encoded in states 1 and 2 of the reward machine. After learning the state-centric options, we decompose them to transition-centric options by partitioning the state space of the environment. As an example, the state-centric options for the reward machine state 0 is decomposed to two transition-centric options that target the reward machine transitions 0 to 1 and 0 to 2. While executing a transition-centric option, its self-transition from the current reward machine state is maintained until the target reward machine transition is triggered by satisfying the labeled Boolean formula. After acquiring the transition-centric options from the training tasks, we can use them to solve a wide variety of novel tasks in zero shot. To solve the test task finally X, and finally would, which means first get X, then would. We first apply the transition-centric options learned from the first training tasks to progress the reward machine state from initial state 0 to 1 through the transition not would and X. Then we apply the transition-centric option learned from the second training task to progress the reward machine from state 1 to the accepting state 2 through the transition would. During execution, LTL transfer aborts whenever the learned options are not sufficient to solve the test task to preserve safety guarantees. Results in simulation show that compared to previous methods, LTL transfer achieve higher success rate across different test tasks and never violates a safety constraint. We deployed LTL transfer at the task planning level of a quadruped mobile manipulator. We learned policies from 20 training tasks, then transferred to 100 novel tasks in zero shot with a 100% success rate. We demonstrated 50 of the test tasks on the physical robot.